Great, thank you very much. And yes, I will be speaking about geospatial inference, protecting convoys, protecting assets, static and dynamic, identifying high-value target locations tomorrow. Today, I'll be giving you some of my thoughts on cyber. And I'm going to start, General Pant started by talking about geographic information systems and its relationship to cyber. I'd like to say that, many of you, very distinguished military officers from all three air, sea, and land forces, understand the terrain of your domain very well. You understand in your specific area of expertise, you understand elevation maps, soil maps, vegetation maps, etc. I'm going to start today by giving you a little bit of terminology, and the work I've done in cyber sort of spans detection of attacks. It's a very technical work. Detection of attacks, both known and attacks that you've not previously anticipated or seen before. And I'll explain what I mean by that. How can we monitor it, and where's the state of the art in terms of scaling this to the vast volumes of transactions that you see? So if you use Microsoft Word, it was probably not developed under your authority or under the circumstances and conditions you may have wanted software developed under your authority to satisfy. Almost all software that you see today has vulnerabilities in it, almost all commercial software, independently of which company you're looking at. What this means is, just as a house has doors and windows and holes in it in places that might allow mice or termites or other things to get into the house, that means that these pieces of software have vulnerabilities that can be exploited by an attacker. And that is the rationale for the two terms that you see defined on this slide. Vulnerabilities, known problems with software that causes that software not necessarily to be breached by an attacker, but to use the functionality in that software for a purpose that was unintended by the person who designed the software. So in other words, this piece of software might work perfectly well for the types of inputs that the user or the programmer who developed it had in mind, but when you feed it some slightly different inputs, it behaves in a completely unintended and potentially harmful way. That's what a vulnerability is. Good news, up to a point. There's something called the U.S. National Vulnerability Database, NVD, developed by the National Institute of Standards and Technology in Gaithersburg, Maryland, about 15 minutes from my house, which is the most extensive known database of vulnerabilities that's at least available online. They describe vulnerabilities, technical details of those vulnerabilities. I looked at it just before coming here, over 56,000 of them, but mostly restricted to well-known pieces of software, okay? Out of the millions and myriads of pieces of software out there that are not widely used, those may not be reported in the database. There are other databases, of course, that also contain this. An exploit is a piece of code written by a hacker usually that exploits one or more of these vulnerabilities in ways that allows them to compromise the system. Plenty of exploits available on the internet. Okay, scary part. We've all heard about platform as a service, infrastructure as a service, software as a service. Well, exploits as a service are out there in the world today. If you know where to look, you can buy exploits for relatively small prices to relatively large prices, which an individual might not be able to afford, but which are very small for a country or nation states. If I was to launch a social media attack, it doesn't have to be me, but a reasonably competent programmer today with at least a master's in computer science, he would be able to launch it using off-the-shelf tools for probably under $1,000. That's a scary thought. The other scary thought, just as Google was formed by two guys working in a garage who were able to disrupt the entire tech industry through dramatic new innovations, it is possible for two guys sitting in a garage somewhere else to disrupt a national cyber infrastructure. So that's the scary part. I'd like you all to keep that in mind. I'm going to move a little bit. I'm a technologist, and I'm going to move a little bit into technology and say, look, Most work on cyber has focused on known attacks. How do I detect attacks that I know about? How do I build models of attacks? How do I build models of viruses and how viruses will propagate? How do I build models of other kinds of malware? I'm going to talk about the fact that for a robust cyber defense, you need to keep track not only of known attacks, but also known normal behaviors. Otherwise, you will not be able to distinguish when you see an abnormal behavior, whether it's good or bad. I'll come to this point later. But all of this is work that's been done in my lab. The yellow things are things that are still in progress. The green things are things that exist. What we have are, we need to know about attacks that are known, and we need to defend against attacks that are known in much the same way as in the US. When you go to an airport, you're asked to remove your shoes, you're asked to remove your jacket, etc. Those are known attacks that you need to defend against robustly. But you also need to know known good behaviors so that you can draw inferences about sequences of events that you see that are unexplained by any of the behaviors that you have in your repertoire. So in other words, if I have 1,000 attacks that are known attacks and 1,000 known behaviors that are normal, when new things come in, I need to know whether these are recognized by the system as being good or bad. If not, they are unexplained, and that's something I'm going to leverage in order to figure out how to dynamically build my database of known and unknown events so I can recognize unknown and unanticipated threats when they occur. So what we've done is built out technology both to detect known activities in a highly scalable manner as well as try to detect unexplained activities. Let me start a little bit with technology. I promise not to go through the details. In most of the cyber world, known attacks are represented in one of a few formalisms. I picked one here today called an attack graph. An attack graph consists of a bunch of nodes like those shown in this picture, which has conditions, preconditions for a vulnerability to be exploited, and the post-conditions that resolve when after the vulnerability has been attacked. So in this graph, for example, you could say that the C's are conditions, the V's are vulnerabilities. I don't know how well you can see it, but the greenish nodes on the left are conditions. Oh well, this doesn't seem to work. The blue rectangular nodes are vulnerabilities. So for example, when you look at this node towards the bottom, V4, it says that C4 and C5 are both needed to be true to exploit this vulnerability. You can't exploit it if you've just got C4 done. You satisfy condition C4. If you're an attacker, you've established condition C4. That's not enough to exploit this vulnerability. You need to get something else in place before you can exploit it. You can also represent this by getting rid of the conditions and making it simply a chain, not a chain, but a graph of vulnerabilities. And there are many, many versions of these. To scale these, remember I said that the National Vulnerability Database has about 56,000 vulnerabilities in its database. There are other databases. There's a large database called Snort Rules, which look at network attacks, which also has thousands of rules that can be represented in this form. Anybody who tries, however, the throughput, we heard this morning from somebody who's defined big data. I forget who the speaker was, but he said what's relevant is not the amount of data, but the rate at which data is flowing through your system. So if you're trying to protect your network, there are thousands of packets flowing through your system per second, in many cases millions, okay? So you've got to be able to track what's going on in those packets in order to defend your system even from known attacks, which is what I'm going to discuss first. So what we did was we said, well, if I've got these graphs representing multiple possible attacks, one graph for each attack, I'm going to be extremely stupid if I try to take this set of attacks and process them one at a time. Instead, we're going to take the set of attacks, merge them into a supergraph which leverages commonalities between the attacks so that you don't check for multiple things multiple times and stitches them together in a way that scales up. Now, So the first problem is how to monitor huge volumes of traffic, and the second is how to identify unexpected activities that you did not know about in the past and add them to your activity database. So you need models of both. We developed a system called PASS, which currently looks at 500K transactions per second, between 5 and 600K, but reliably 500K plus transactions per second on an 8-node monitoring cloud, okay? So not a super fancy cloud, and I think we now have methods that hopefully by the end of the year we'll be able to show scales that by another factor of about 10, okay? So hopefully about 5 million, with a small loss of accuracy, I should add. So one of the things I distrust is when somebody tells me they're gaining speed and not giving up anything, I usually worry about it unless they tell me they've also increased the hardware, okay? So you usually lose something when you scale something up substantially. The question is how to make that. We've also demonstrated the ability to identify unexplained behavior. I'll talk about that in a minute, with precision over 80% and recall over 70%. I'll explain what I mean by that. So suppose I now have a set of known activities, some good, some bad. By the way, good doesn't mean it's beneficial for mankind. It just means it's not bad, not malicious, okay? So some good activities, some bad activities. When I see an observation stream and it contains some not necessarily contiguous sequences of events that are monitored that do not fit any of the patterns of either the known or the unknown activities, then it's something that's unexplained. These are the types of activities I knew about to start with. None of them is consistent with what I'm seeing. That tells me that what I'm seeing is unexplained by the models I currently have. This means that when you see something unexplained, you can do one of two things. You can predict how unexplained it is, one. You can identify what we call a distance between the observed behavior and known harmful activities versus known good activities, and use that to predict whether it's more likely to be malevolent or more likely to be not so. Or three, you can use user feedback, analyst feedback, to tell you, hey, this may have been unexpected. We didn't have models for this before, even though it's a known activity. It's a known activity intuitively, but it's not in the system. So we're just going to push a little button saying it's a known activity. The system can look at these known activities and automatically learn a model for these previously unclassified activities and say, okay, we've now extended our database of known and unknown activities. There's also a lot of work that's been done. So unexplained, I should emphasize, does not mean bad. So what this allows you to do is by tracking variations between what you see and the models you've learned, you can learn new models and expand your repertoire, thus allowing you to have a continuously learning system. This is necessary because we know that new kinds of attacks are invented every day. Here's an example, very simple example. The little graph in green at the top left is a normal activity, a good activity. The one in the middle, in sort of a beige-ish color, is, let's say, a suspicious activity. And this line here shows me the transactions that I've seen. Okay, so just a very small example. You can automatically detect that the FTP login, the FTP get, and the FTP close subsequence of the sequence of transactions that may have been noticed at some server is an instance of a normal activity, the one on the top left, which corresponds to the path FTP login, FTP get, FTP close. And likewise, in this sequence, you also have some suspicious activities in the same way. But also, there are some subsequences in there that are partially unexplained, okay, or totally unexplained. And that means that they don't correspond intuitively. I'm not going to go through the technical details, but they don't correspond to any of the behaviors that either of those two graphs would predict. So that's what we're trying to do. We tested this out using data from a university, network traffic data from a university, not mine. And we used as attacks these snort rules that I talked about earlier. Now, we then said, okay, how do we test how accurate we can get? Because what does unexplained mean from the point of view of verifying? We've got a technical definition of unexplained, but how do we check whether that's right or wrong? So what we said was, well, we're going to randomly remove some rules, some of the snort models, all right? So when I had my snort models, all of them, I detected certain instances of them using my known models, right? These are all known models. I could use the known model detector and find instances of these. Now, if I remove some of these known models, the instances of those known models which were removed should not be explained anymore by what's left behind, because the models that explain them have disappeared. How accurate can you get? So generally speaking, depending on what we ignored, we got numbers, I would say, around 80%, okay? Some go down. Actually, by the way, of each of the charts that you see here, the tau variable is a parameter we were trying to test against. We were trying to see what parameter setting gives us the best results. So the only ones you need to look at in the top two tables are the first row with tau equal to 0.4, and likewise for the two tables at the bottom. Okay? These are slightly different definitions of what we mean by unexplained, but you can see that the numbers basically are around 80, which in the prediction business is about as good as you're likely to get. Okay? So I've very rarely seen consistently replicable prediction results on almost anything that go above 80% in virtually most domains. Okay, I'll skip some of this and go to a real-world example. I decided I wouldn't name the country in this real-world social media attack that happened. This is a very specific kind of attack that's been emerging over the last few years with obviously the explosion of use of social media. This is an attack that occurred in a national election in a major country during the last few years. At one point, protesters gathered in a central square to protest what they saw or what they claimed was a highly unfair election process. By the way, I don't really have a position on this. I'm just telling you what happened. I'm not saying what happened was good or bad. I'm just telling you how things can be manipulated. Shortly thereafter, several hundred protesters were arrested after this. Protesters then started screaming bloody murder on Twitter and social media channels, but primarily Twitter. If you track the hashtags on Twitter that related to the protest, there were about 20 of them which were what Twitter would call highly trending topics. There were things that suddenly experienced a dramatic upsurge in discussion on Twitter during a very, very short period of time. Okay, somebody was watching this very, very closely. I don't know who, though there is no shortage of people who've taken a guess on who. But I really don't know who. But literally within a couple of hours of the protest trending very highly on Twitter, there was a massive social media attack launched in retaliation. Over 25,000 Twitter accounts launched the attack. These were attacks launched by Twitter bots, and over 400,000 tweets were launched. By the way, I do want to say that this chart and the statistics on this chart are not from my lab, but by another research group in the US which studied this particular attack in greater detail. Okay? The protest was completely shut down. Now, let me just actually go back to the slide for a minute. Now, you can imagine the same thing happening, not with an election, but with, let's say, a national security issue which comes up in a country. I mean, you can all think of many going on right now, but there's a national security issue that's going on somewhere, and if a foreign nation state decides to interfere in the process by skewing opinion one way or the other, you better have a good way of finding out. One, that it's happening, that there's fake injection of a social media attack into the social media social network, and B, who it is. I'm going to sort of just, this is my slide now. using the data from the previous slide, which somebody else did. I'm going to sort of quickly assess this in terms of terms that are more familiar in the military domain, the traditional kinetic military domain, and give them a grade, okay? I don't know what the precise, I know the intent of the people who launched the attack was to disrupt the protest. I do not know whether they intended that to be known or not known. If their intent, the intelligence preparation of the battlefield was very well done. It could have been done better, but these 25,000 accounts were largely present 6 months before the attack occurred. They were there, they were somewhat active, but not hugely so. 6 months before the attack occurred. So I would give them at least a B on that. Situation awareness and surveillance of the battlefield, they scored an A on this, clearly. They were out there hammering the protesters on social media immediately after the protests reached a threshold point. They were monitoring it, they knew what was going on, and they launched the social media attacks. Okay, what about power projection? I rate this a little lower, mainly because in any cyber attack, in most cases, the attacker wants to come, do whatever he wants to do, and leave largely undetected, in most cases. This was a very easy attack to detect. It didn't require, several US PhDs to figure this out. Very easy attack to detect. The fake accounts were very easy to detect. Many of them were on known lists of malware providers and propagators and spammers. So they did an excellent job in influencing the discussion, but did not cover their tracks well. I could think of much better ways of launching this attack, which I, of course, do not plan to go into, than was done here. And that's sort of the, D did not get out, sort of a continuation of the previous bullet. The assets were not reusable. They had all these bots, but they were not reusable. They came in once, did their job, and were done. So, bottom line, social media attacks can destabilize decision making by a country by providing a false picture of the degree of protest or positions for or against a particular topic. So if somebody wanted to come in and destroy, let's say, an Indian government initiative, they could try to do this by launching an attack that that gave the appearance of large volumes of people who were opposed to that on social media. If they were undetected, that might actually skew the perception you have of what's true and what's not. Where are we headed now? I want to wrap up. Well, we've done actually a ton of other work, which I don't have time to talk about, but on cyber. But I'm going to talk primarily about the two things we want to do, and we've made some progress in, but not completed. One, automatically learning models of activities, good or bad. Remember, I want to know both good activities and bad activities. Because once I detect an activity, if I know it's good, I do certain things. If I know it's bad, I do certain other things. But I need to be able to detect the activities, which relies in turn on having as large a repertoire of activities as possible. So we're building learning algorithms to learn activity models automatically using a bunch of semi-supervised techniques. That means you have some training data, but then you learn from it automatically. We're trying to detect unexplained activities. Unexplained activity detection is still not as scalable as we would like. That's something we're trying to scale right now. So with that, I think I'll stop and thank all of you for listening to me. Thank you.